Good morning, students. Welcome in new lecture of Math F242 Operation Research. In last class, I was discussing about the problem 6.7 series system and problem 6.8. So, I have given you idea about the series system. The series system having n components arranged in series. What is the significance of this series? That if any components fail, then the complete system will fail. I trust audio video is okay.
Yes, sir.
Thereafter, I have started the derivation for computing the reliability of the system. So let us have quick recap of this. So initially, I have assumed the life length of a component as a xi, right? Fi, capital Fi are the PDF and CDF. Ri and Zi are the reliability and hazard rate function for the component I. Then after, we assume that let y is the life length of the system, which is equal to minimum of x1, x2, xn. And it is given to you all the components are independent to each other. Now we have to compute the PDF, CDF, reliability and hazard rate function and the mean time to failure of the system. So we know that what is the reliability? Reliability is P of y greater than t. So using this, we have computed that reliability of the system is nothing product of the reliability of the component. Then after we have we have taken the logarithm, then differentiate. So when we differentiate, here you are getting the PDF of the system. PDF of the system in terms of the reliability of the system, PDF of the component, and reliability of the component. And we know that Ft upon Rt is equal to Zt. So using that approach, we have computed that Zs is equal to summation of Zit, that is hazard rate function of system is equal to hazard sum of hazard rate function of the components. Thereafter, we have computed the CDF of the system, right? The CDF of the system. So here we have computed the CDF of the system as a Fy pi 1 minus RIT. Then after, in question number 6.8, consider n component independent series system. We have the n component independent series system, means all the components are working independently. Given that these components have the constant failure rate lambda 1, lambda 2, lambda n respectively. So what the information is given to you, that here we have the xi, or you can say instead of the xi, you say that zit. Zit is given to you as a lambda I, a constant, where I is equal to 1, 2, and n. So when the zit is equal to lambda I, it is constant. You know that what is the RIT? RIT by the theorem 6.2, e to power minus Zs ds. So Zis ds and 0 to t. So e to power minus 0 to t lambda I into ds. So it will be the e to power minus lambda I into t. So RIT is equal to e to power minus lambda I t, and FIT for the component. So it is the ZIT into RIT. ZIT is given to you as a lambda I, and RIT just now we have computed e to power minus lambda IT. So from here you can see that xi follow the exponential distribution with parameter lambda I. Then after reliability and FIT we have computed, and E of Xi. E of Xi, that is the mean life length of a component. So you know it is the 0 to infinity of RT dt. So for the component, it will become the RIT dt. So 0 to infinity e to power minus lambda it into dt. So this will give you e to power minus lambda it upon minus lambda I 0 to 0 to infinity. So this will give you 1 upon lambda I. And let's say it is the mu I. So so here we have the failure rates lambda 1, lambda 2, lambda n respectively. Find the reliability of the system. So when we have to compute the reliability of the system, so just now we have seen RST. RST is what? Product 1 to n of RIT for Sri system. For Sri system, we have seen reliability of the system is equal to product of the RIT. So it will become e to power minus lambda 1 t, e to power minus lambda 2 t, and e to power minus lambda n t, which can be written as e to power minus lambda 1 plus lambda 2 plus lambda n into t, where t greater than 0. So this is the reliability of the system. And we know that if you differentiate, it will give you minus lambda 1 plus lambda 2 plus lambda n e to power minus lambda 1 plus lambda 2 plus lambda n into t, and FST, reliability of the system, minus of RST, and this will become lambda 1 plus lambda 2 lambda 2 plus lambda n into t. So this you can say that y means lifetime of a system follow the exponential distribution with parameter lambda 1 plus lambda 2 plus lambda 3 and lambda n. So here we have the PDF of the Sri system, hence prove that failure rate of the system is also constant and is equal to the lambda 1 plus lambda 2 plus lambda n. So here we have proved this when we are saying that it is the parameter. So parameter is what? It is the failure rate. Failure rate, and it is the sum of the constant quantity. So this implies it is the constant and equal to lambda 1 plus lambda 2 plus lambda n. What is the lifetime distribution of the system that we have computed? It is exponential. Also express the mean lifetime of the system mu s in terms of the mean life length of the mean life length mu1 mu2 mu1 of the components. So now we have to compute the mttf of the system mu st, right? That is the mttf. So mttf, you know what is the mttf? mttf is 0 to infinity of rst into dt. So this will come 0 to infinity. Rs we have computed for the Sri system as e to power minus lambda 1 plus lambda 2 plus lambda n into t. So e to power minus lambda 1 plus lambda 2 plus lambda n into t into dt. So its integration will be e to power minus lambda 1 plus lambda 2 plus lambda n upon lambda 1 plus lambda 2 plus lambda n minus, and here we have the 0 to infinity. So what this will give you, 1 upon lambda 1 plus lambda 2 plus lambda n. And in starting, I have computed the mean time of a component. So mean type of the component, mean time of to the failure of component is the mu I is equal to 1 upon lambda I. So this can be written as lambda I is equal to 1 upon mu I. So this can be written as 1 upon mu 1 plus 1 upon mu 2 plus 1 upon mu n, or it is the 1 upon summation I from 1 to n of 1 upon mu I, or it is the inverse of 1 upon 1 upon mu I, summation of the 1 upon mu I. So this you have computed the mean life length of the system in terms of the mean life length of the component. Right. So this we have for the series system. Right. So we have computed that a series system failure time also follow the exponential exponential distribution. This we have computed, mu I we have computed, and mu s we have seen that it is the inverse of summation of the 1 upon mu I. So this we have done. So now next arrangement is the parallel system. So what is the meaning of the parallel system? Next arrangement is parallel system. Next arrangement is the parallel system. Parallel system of n components. N components. So here, what is the meaning of the parallel system? Here we have the first component. Here we have the second component, third component, n minus 1 component, and n component. Here, each component is arranged in parallel. Each component are arranged in parallel. And what is the benefit of this parallel arrangement? If means whole system will fail only when all component all component fail. Right? Means if the first fail, then second fail, then third fail, then fourth fail, then all fail. So when all will fail, then only we will say system fail. Right. So that is the parallel system. So in general, in houses, we have the fuse system like this. Right. We have the fuse system like this. So just failing of one fuse, not necessarily fail the electricity in whole house. Generally, we have the failure in one room only. So here we have the parallel system. So the in this also we have the two question 6.9 and 6.10. So let y denote life of an independent parallel system with n component. Find the PDF and CDF of the y. Hence, otherwise, prove that exponential of minus hu du is equal to 1 minus product of 1 minus exponential of minus hiu du. All integration performed from the 0 to t, where ht is hazard rate of the system and hit is the hazard function of the ith component. So this is the question number 6.9 and 6.10. Consider the system consisting of n components arranged in parallel. Assume that component function independently and have a constant failure rate lambda. All the component has the same failure rate lambda. Then find the PDF and mean life of the system. So you have to determine the PDF and mean life of the system. So main thing here, what we have, the arrangement of the components are in parallel. So when we have the parallel, and I'm saying that the system will fail when all the components fail. So what is the meaning of this? What is the meaning of this? Yes, what is the meaning of this? Yes, I'm saying that if let let y is the y be lifetime of parallel system of the parallel system. So what and whatever we assume for the series system means xi, the life length of the lifetime of ith component, it is the continuous random variable. So continuous random variable means characterized by the PDF, characterized by the CDF, right, having the reliability RIT and hazard rate function ZIT and hazard rate function ZIT for the ith component. So I was talking what is the relation between the y x1 x2 xn. So anyone please
Maximum
yeah,
maximum of x.
maximum of this, right? Good. So here for the parallel system, because the system fail when all components fail, so the maximum of the x1 x2 is equal to the life length of the system. Now we have to compute the reliability, all other parameters for the parallel system. So we have to compute the first reliability of the system. So reliability of the system, you know what is the meaning of the reliability of the system. If you have to compute RST, so by definition, it is what? Probability y greater than t. By definition, it is the probability y greater than t, or it is equal to 1 minus probability y less than equal to t. It is equal to 1 minus probability of y is what? Maximum of x1, x2, xn less than equal to t. So when the maximum is less than equal to t, this implies all are also x1 less than equal to t, x2 less than equal to t, and xn less than equal to t. So if the maximum is less than equal to t, this implies that all are also less than equal to t. So what is the meaning of this? This is the 1 minus, it is the joint probability. So it is equal to 1 minus 0 to t, 0 to t, 0 to t, n time integration of fx1, x2, xn of x1, x2, xn, dx1, dx2, and dxn. So since since x's are independent, if x's are independent, you can write the joint density in terms of the marginal density. So it will become the 0 to t f of x1 x1 dx1, 0 to t f of x2 x2 dx2, 0 to t f of xn xn dxn. So 1 minus, this can be written as 1 minus t to infinity of fxi x1 dx1, 1 minus t to infinity fx2 x2 dx2, and 1 minus t to infinity fx2 xn xn dxn. So 1 minus, this is what r1t, this is what r2t, and this is what rnt. So it is the 1 minus product from 1 to n of 1 minus RIT, where RIT is what? Reliability of the component. So this is the reliability of the system. So reliability of parallel system is equal to 1 minus product from 1 to n of 1 minus RIT. Clear? Or any doubt? Now we have to compute the PDF. So this can be written as product from 1 to n 1 minus RIT is equal to 1 minus RST. Taking logarithm on both sides, taking logarithm on both sides. So this will become summation from I is equal to 1 to n of 1 minus RIT is equal to ln ln of 1 minus RST, ln of 1 minus RST. So when we differentiate with respect to t. So when we differentiate with respect to t, what you will get? You will get the summation yes, from here what you will get? Summation I from 1 to n 1 minus RIT minus of RIT dash t is equal to 1 upon RST dash. RST dash. So, and here we have the minus, and we know that minus of RST is what? FST, since FST is equal to minus of R dash T. So FST upon 1 minus RST, and I is equal to 1 to N FIT upon 1 minus RIT. So this implies FST is equal to what? FST is equal to 1 minus RST summation I from 1 to N FIT upon 1 minus RIT. So that is the PDF of the system. And from here only, from this result only, we can derive another one important result. Right? We know that, or from here, not from this side, from this side. So we know that in this that will not work. Okay, in this that will not work. We have seen. Let us start with the new one. RST is what? RST, reliability of the system. Reliability of the system is what? It is a product from 1 to N of 1 minus RIT. 1 minus RIT, 1 minus product of 1 minus RIT. This we have seen. And we know that what is the relation of the RST and ZST, or failure rate function. So RST, you know, it is the e to power minus 0 to t ZS, right? ZST dt, or you can say ZS ds, is equal to 1 minus product from I is equal to 1 to N 1 minus. Now what is this? E to power minus integral 0 to t ZIT dt. ZIT dt. So that is the relation between the hazard rate function of system and the component. So it is written here. Let Y denote the life of the n component parallel system with n components. Find PDF and CDF of Y. Hence or otherwise prove that exponential of integral 0 to t minus hu du is equal to 1 minus product of 1 minus exponential of minus integral 0 to t hiu du. The same thing we have proved here. Right? The same thing we have proved here. Instead of the h hazard rate, we have written the z. Right? The same thing here we have. Now we have to compute the CDF. So when we have to compute the CDF, what is the meaning of the CDF? CDF is what? If you,
Here we can write it as 1 minus Rs of t.
yes, good. So CDF, if you have to write the CDF of y means Fy y. Fy, it means it is the probability y less than equal to, or or less than equal to y, or you can say fyt better you assume, because we are assuming has a time. So probability that probability y less than equal to t, that is the 1 minus probability of y greater than t. So this will become 1 minus rst, 1 minus rst, and 1 minus rst here, 1 minus rst at this place can be written as product of the 1 minus rit. So this is equal to product from 1 to n of 1 minus rit. So that is the CDF of the life length of the parallel system. So that is the first question. In the second part, in the 6.10, consider a system consisting of n components arranged in parallel. Assume that components function independently and have, all the components are functioning independently and have constant failure rate lambda. Find the PDF mean life of the system. So it is given to you here, ZIT is equal to lambda, not lambda I. It is a lambda given to you, and it is the constant. So when the ZIT is given to you as a lambda, so what is the RIT? RIT is the e to power minus integral 0 to t ZIT into dt. So many times we have done. So directly I am writing e to power minus lambda t, and if you differentiate f ft is what? Ft is or fit is what? Minus rit dash. So that will give you lambda e to power minus lambda t. So this implies that xi follow the exponential distribution with parameter lambda, right? This implies that xi follow the exponential distribution with parameter lambda. And from here, if you compute the value of exi, that is the mu I or mttf, so we have computed many times, so it is equal to 1 upon lambda, right? So for the component, for the given constant failure rate, we have the following data. Now if you have to compute the reliability of the system, so reliability of the system, RST, you know, it is the 1 minus product from 1 to n of 1 minus RIT, 1 minus RIT. So 1 minus product 1 to n 1 minus e to power minus lambda t. So you have to product the 1 minus e to power minus lambda t n times. So it will become 1 minus e to power minus lambda t power n. Clear? So this is the reliability of the parallel system having n components, right? Having n components with constant failure rate. Now, if you have to compute the FST PDF of the system, so we know that it is the RS negative of the R dash T. So when we differentiate minus of, so minus n 1 minus e to power minus lambda t to power n minus 1 and minus e to power minus lambda t and minus lambda. minus lambda. So on combining, so on combining, it will become the n lambda e to power minus lambda t 1 minus e to power minus lambda t power n minus 1. Now,
Excuse me, sir. Excuse me, sir.
huh?
Sir, it will be e power minus lambda t times just minus lambda. No need minus in front of e.
एक मिनट. This will not come. This is the linear one. This will not come. Minus lambda only. Right? N lambda 1 minus e to power minus lambda t to power n minus 1. Now, if you have to compute the FST, so probability y less than equal to t. So it is the 1 minus probability y greater than t. So 1 minus RST, right? 1 minus RST, and it is equal to product of product 1 to n of 1 minus RIT. And we have already computed this as a 1 to n 1 minus e to power minus lambda t, which can be written as 1 minus e to power minus lambda t to power n. So that is the PDF CDF of the failure time distribution of the parallel system. Then after, we have to compute the mu s or ET. So here we have ET, you say, or E by you can say, means expected mean life length of the system. So what is this? It is the 0 to infinity of RST into dt. And RST we have computed as 0 to infinity, and this we have computed as RST 1 minus 1 minus e to power minus lambda t power n into dt. So let 1 minus e to power minus lambda t is equal to p. So this implies e to power minus lambda t is equal to 1 minus p, or minus lambda t is equal to ln of 1 minus p minus lambda dt is equal to minus 1 upon 1 minus p into dp. So if it is the mu s also, so mu s can be written as mu s will become integral, what will come 1 minus p to power n, what is the dt is 1 upon lambda 1 minus p into dp, please help me, and limit will become 0 to 1. Correct? Please check the limit and everything.
Yes, sir. 0 to 1.
Yes. So this can be written as 1 upon lambda and integral 0 to 1 1 minus p to power n upon 1 minus p can be written as
1 plus
1
p
plus
plus
p plus p square plus p to power n minus 1 into dp. So 1 upon lambda integration will become the p plus p square by 2 plus p cube by 3 plus p to power n by n 0 to 1. So it is equal to 1 upon lambda 1 plus 1 by 2 plus 1 by 3 plus 1 by n. So that is the mean lifetime of the system. Clear? So in this way, whatever the given information, accordingly we have to proceed, right, to determine the required things. So here we have the detail of the all these things, whatever we have discussed till now. Clear? FST we have computed, then FYT, PDF, CDF we have computed. If failure rate is given to you as a constant, then we have computed this as a, or you can say if you have to write in terms of the mean life length of the component, then will become the mu 1 plus 1 by 2 plus 1 by 3 plus 1 by n. This will come. Now, it is a book problem 6.13. We are required to find the overall reliability of the system. So, from the above figure, what is the arrangement of these subsystem?
parallel.
It is
Each is
the
parallel
parallel.
and
Here,
series.
the component 1 and component 2 are arranged in parallel. Component 3 and 4 are arranged in parallel. Component 5 and 6 are arranged in parallel. Let it is the subsystem 1, it is subsystem 2, it is subsystem 3. So subsystem 2 and 3 are arranged in series, right? Let this is the subsystem 4, and subsystem 1 and 4 are arranged in parallel. So here we have this system. So 1 and 2 are being in parallel. Their cumulative reliability, because we have the parallel system, right? So its reliability will become 1 minus R1 into 1 minus R2. Similarly, 3 and 4 are in parallel. So reliability of the subsystem will become 1 minus R3 into 1 minus R4. Similarly, component 5 and 6 are also in parallel. So 1 minus R1, 1 minus R5 into 1 minus R6. Now, the subsystem of 3, 4 and 5, 6 are in series. So reliability of 3, 4, 5, 6. 3, 4, 5, 6 will become, right, R of 3, 4 into R of the 5, 6. R of the 5, 6. And R of 3, 4, 5, 6 is parallel with R12. It means net will be, they are in parallel, right? So net reliability will become the 1 minus 1 minus reliability of 1 2 into 1 minus reliability of 3 4 5 6 3 4 5 6. So here total reliability we have, right? Clear? So 1 minus, this is the reliability of 1, 2 into 1 minus reliability of the 3, 4, 5, 6. So here on solving, you will get this. This is a very important question. We have to determine, we are required to find the overall reliability of the system. Here the system are arranged in this way. Means 1 is attached with the 2 as well as with the 4. 2 is attached to the 3 and 4. 3 is attached with 1 and 2. 4 is also attached with 1 and 2. So if we have this system, so this system can also be judged as, let this is the 1, this is the 2, this is the 3, this is the 4, and so on. So 1 is related to 3, 1 is related to 4, right? 2 is related to 3, 2 is related to 4. So the above system can be reconfigured like this. So now, whatever the new system, new configuration I have drawn, in that 1 and 2 are parallel, 3 and 4 are also in parallel, and these subsystems are in series. So here we have drawn, now this reliability system given in question can be represented by this. Clear this part? Only the important thing is this: from this figure, you have to reconfigure in series parallel system. Initially, it is not looking like a series parallel system, but now after the reconfiguration, we have the series parallel system. So then R12 are in parallel. So reliability will be the 1 minus product of the 1 minus RIT. 3, 4 are also in parallel. So here we have computed the reliability 1 minus R3 into 1 minus R4, and subsystem 1, 2 and subsystem 3, 4 are in series. So net reliability will come product of the RIT. So subsystem 1, 2 into subsystem 3, 4. So this will give you the reliability of the system. It will give the net reliability of the system. Let us have a system has the 5 identical components, means same component, connected in series. If it is desired to have the system reliability 0.95, how good should be the reliability of each component? What is given to you? They are in the series system. So RST is equal to product from 1 to n of the RIT. Right? All the components are same. So this will become the RIT power 5. If there are the 5 components, so it will become the RIT power 5, and it is the RST. And how much the RST we want? We want it should be the 0.95. So RIT will become the fifth root of the 0.95. Right? So here P will come the 0.98975. We assume P is the reliability of the component, then RST will become the P to power 5, and it is desirable that reliability should be 0.95. So P will come 0.98975. So that much reliable component we have to arrange in series to get the reliability of the system 0.95. So here I am stopping. Now few examples only remain. So in next class we continue. So Now time for the recheck is over. So now onward, I will not take. So I will start the recheck. Then after I will tell you what is the update.
So what is the average of midsem?
I think it is 36 point something.
Okay, sir. Thank you.
I will update. I will update after the recheck. I will update the final average.
Okay,
But
sir.
around either 34 something or 36 something.